Okay. In Module 4 of Week 11, we'll extend our ideas about heat and phase change, heat and heat capacity to study phase changes and latent heat. Okay. So what I'm showing you here is a phase diagram for water in the pressure P, temperature T plane. So this is high temperature and this is high pressure. And you see the three typical phases of any material: solid, low temperature solid, intermediate temperatures and pressure liquid, and then a gas at higher temperatures. Okay. And so we could start our water in some initial state at, say, 1 atmospheric pressure, okay, and say room temperature of 20 degrees Celsius on our graph. And so that water exists in a liquid state. And the question is, well, how hot can we make the water? How high can we raise the temperature while still maintaining the water as a liquid? And well, heating will occur as I add heat to the system. According to the change in temperature will rise according to the heat capacity and the amount of heat I add to the water. And so initially, I can heat the water up, adding an amount of heat Q, which will lead to a temperature change delta T according to the heat capacity of the liquid. That's the 4,186 joules for water. Okay. And then what will happen is I'll get up to like 100 degrees centigrade, and then I'll convert into the gas. But before I actually convert completely into the gas, I need to keep adding additional amount of heat, some additional heat in addition to this amount. And what this heat will do is it will convert the liquid into a gas, but this entire process will take place at a fixed 100 degrees Celsius. So there's no temperature change while I add this heat. So this is a kind of a new process. And then once I've added a certain required amount of heat, then the entire system will be converted to a gas. And so how hot can I make liquid water? Well, 100 degrees Celsius. Once I go slightly above 100 degrees Celsius, after adding this additional heat here, I've converted the water completely into a gas. And then once I do that, the temperature starts to rise again above 100 degrees Celsius as the system is now in a gas phase. And so whatever heat I now add to the system goes into raising the temperature of the gas. Okay? And as I go along here, I'm in a gas phase now. And the heat capacity I need to use in this formula is the gas phase heat capacity. Okay? So the new wrinkle here is what happens here when you go through this phase change from a liquid state to a gas state, and this mysterious idea that you have to add heat to the system, but the temperature doesn't go up. Okay? So these phase changes are important, very important in biological system. I mean, one way of heat removal is through sweating. And in sweating, what you're doing is a thin layer of water on your body is vaporizing from liquid water into vapor water in the air. And as we've seen here, in order to vaporize the water, you need this additional heat. And so that's provided by your body. So your body provides the heat to the water, which vaporizes it and takes up that heat and disperses it into the environment. Okay? So you require this heat. And what is this heat? Well, this heat is this heat which vaporizes liquid water from a liquid to a gas is known as latent heat. Okay, and basically this heat is a form of energy which is locked into the structure of the material. And when the structure of the material changes, well, that requires heat in order to change the structure. So the latent heat is the heat which is added to an object which reconfigures the molecules in the material at zero temperature. And so all this energy that you're putting in doesn't go into changing the temperature. It simply goes into reconfiguring the molecules. And so if you start off, say, in a solid phase, in a crystalline phase, in order to break the crystal down into, say, and go into a disordered liquid phase, okay, which is a disordered dense phase of molecules, you need to provide some energy input, okay? You need to add this latent heat. And then to go from a disordered dense liquid into a disordered but less dense gas, you also need to break up the liquid structure, okay, and all the interactions between the liquid molecule. And so that requires a further energy input, okay, just to convert the liquid into the gas or vaporize the liquid, okay. So, if you're going from a solid to a liquid, that energy, the heat that you must add, is called the latent heat of fusion, or, well, LF is the latent heat of fusion. And since the latent heat has units of joules per kilogram, the latent heat is the amount of heat per unit mass. And so you take the latent heat, you multiply it by the mass, and that gives you the amount of heat you need to add to a solid of a certain mass in order to convert it into a liquid, okay, at a fixed temperature given by the melting temperature. And then if you do the same thing going from a liquid to a gas, it's called the latent heat of vaporization. So again, LV is the amount of energy per unit mass that you need to vaporize a unit mass of the liquid. And so taking that latent heat and multiplying it by the mass gives you the total amount of heat you require for that mass of liquid to convert completely into a gas at the vaporization temperature, okay? And it's essentially this latent heat of vaporization, which is what the water on your body is taking in and vaporizing when you cool yourself via sweating. And then finally, another thing is that of course you can go the reverse process. You can go from a gas to a liquid or a liquid to a solid. And if you do that, for the reverse process, the latent heat has the same magnitude but the opposite sign. Okay? So when a gas condenses into a liquid, it actually gives off heat. And when a liquid crystallizes into a solid, typically it will also give off heat, okay, to the environment. And so what are some values of these latent heats? Well, here's a table for various substances. There's the melting point where you go from a solid to a liquid. And here is the latent heat of fusion. Something to keep in note for water, it's 3.34 times 10 to the 5 joules per kilogram, which is important to know. And the boiling point of water here is 100 degrees Celsius. And at the boiling point, you're talking about the latent heat of vaporization, 2.26 times 10 to the 6 joules per kilogram. Again, important quantities to know because the latent heats of water will come up in problems. Another thing to notice here is that the latent heat of fusion of a substance is not equal to the latent heat of vaporization in general. Okay, and this is because you're changing the structure, and going from a solid to a liquid is a different structural change than going from a liquid into a gas. And also notice they're not only different, but they're quite different, right? This is an order of magnitude difference. The latent heat of fusion is here on the order of 10 to the 5, and the latent heat of vaporization is on the order of 10 to the 6. Okay, so let's do a simple example of this. if you see an attractive person, it might make you jealous. It might make your blood boil. And so obviously if your blood is boiling, that attractive person is giving off heat to you. And think about how unfair this is for the attractive person, right? Very, very good looking people are giving off a lot of heat, and that requires a lot of energy. So unfair. Okay. So given that, let's do this problem. So basically, how much heat does it require to boil your blood? Okay, it says here that 8 to 9% of the body mass is blood. And so if you're 60 kilogram person, then 8 to 9% of this is equivalent to about 5 kilograms of blood. Okay, so you're looking at 5 kilograms of blood, and then you want to bring the blood from 37 degrees Celsius all the way to 100 degrees Celsius, where the blood will boil. Okay, so the blood will treat as essentially water. You're boiling off the water. Okay, and so the heat that you require to do this, raise the temperature. So in order to raise the temperature to the boiling point, you require an amount of heat given by M times C times delta T. And here M is 5 kilograms. C is the blood, heat capacity of blood, which is 3,600 joules per kilogram per Kelvin. Okay, it's a mixture of solids and water. And the temperature change here is 100 degrees centigrade minus 37 degrees centigrade. And you can calculate this out, and this is 1.1 times 10 to the 6 joules. Okay, so that's the amount of heat required to raise the temperature from 37 degrees Celsius to 100 degrees Celsius. And then to actually convert the liquid to the vapor, or to boil the water, you require an amount of heat given by the mass of the blood times the latent heat of vaporization, because you're vaporizing the blood. And the mass of the blood is 5 kilograms, and the latent heat of vaporization, well, we'll use that we're vaporizing water, and so I use that value 2.26 times 10 to the 6 joules per kilogram from the table, and I get a latent heat. I get a heat just to boil the blood, which is 11.3 times 10 to the 6 joules. And so if I add these two values together to get the total amount of heat that is put out, the total heat is the sum of these two, is 12.4 million joules, which seems like quite a lot, and it is. The other thing to notice is that the amount of heat required to actually just raise your temperature all the way from 37 degrees up to 100 degrees is only 1/10 of the amount of heat that actually takes you from the liquid to the vapor. And so the latent heat is quite a substantial amount of heat required. Okay, it's 10 times more heat than the entire amount of heat required to raise your blood from 37 degrees to 100 degrees centigrade. Okay, let's do a slightly less silly example. We'll look at how to make a gin martini, and this might be good if you ever become a bartender, and you may sometime in your undergraduate career. You want to make a gin martini, so you take a shot of gin. Okay, a shot is 1.5 ounces, or about 34 grams of gin. Gin has a heat capacity. It's a mixture of ethyl alcohol and water, so it has a heat capacity of 2,800 joules per kilogram per Kelvin. And you take the gin out of the cabinet so it starts off at room temperature. And then you toss into the shot, you toss in an ice cube. The ice cube has a mass. This is 7.4 grams. A little bit of ice. It has a latent heat of fusion, okay? This is its melting of 3.34 times 10 to the 5 joules per kilogram. Okay, that's from our latent heat table. And the ice cube is at 0 degrees Celsius, okay? And so you take the gin and you take the ice cube and you put it in an insulated container so that there's no overall energy loss in the system. And the question is, well, what will the final temperature be? And there are three possible outcomes which depend on the relative amount of gin to the relative amount of ice. So if you have lots of ice but little gin, then you can imagine that you're going to basically end up closer to 0 degrees. Well, you're going to end up basically with the ice dominating. And so what will happen is the gin will actually just cool down to the temperature of the ice. And some of the energy that the gin loses will go into melting some of the ice, okay? Or if you have a very small amount of ice but lots of gin, then the gin will lose the energy, melt all of the ice, and the final temperature will be somewhere, you'll get gin and liquid ice, and a final temperature of somewhere between 0 and 20 degrees Celsius. And then if you want to make the perfect gin martini, you use just enough gin to melt the ice melts, the gin goes down to 0 degrees Celsius, the ice is at 0 degrees Celsius, and you reach thermal equilibrium. And that's a really cool gin martini. Okay? Now note the gin again is losing energy by exchanging heat and giving it to the ice and water. So the gin loses energy and the ice water will gain energy in this problem. Okay? So in this example, we might want to start off by considering how much heat must be expelled from the gin to cool the gin from 20 degrees Celsius down to 0 degrees Celsius. And so the heat required is the mass of the gin times the heat capacity of the gin times the final minus the initial temperature. So that's the 3.34 grams times the 2800 joules per kilogram per Kelvin heat capacity times the final temperature of 0 degrees Celsius minus the initial temperature of 20 degrees Celsius. And that gives me a heat of minus 1904 joules, which means that the gin is actually losing heat or losing energy to the water. Okay? And now, is this enough heat to completely melt the ice? Well, you have to then consider how much heat must be taken by the ice to melt the ice fully, okay, resulting in liquid water. And so that is given by, that amount of heat is given by the mass of the ice times the latent heat of fusion of the ice. So the ice was 7.4 grams or 7.4 times 10 to the minus 3 kilograms. And the latent heat of fusion of ice from the table is 3.34 times 10 to the 5 joules per kilogram. And so to totally melt 7.4 grams of ice requires 2,472 joules of energy. And so the gin is not giving up enough energy to fully melt the ice. And so what happens instead is that the ice partially melts. And so you end up with ice at 0 degrees Celsius in equilibrium with gin at 0 degrees Celsius. Okay, or a gin, ice, water mixture, and there is some water because of the partial melting at 0 degrees Celsius. So by partially melts, you might ask, well, how much ice melts? And you can do this by just doing the ratio of the heat. So you require 2,472 joules of heat in order to totally melt the ice, but you're providing the ice with only 1904 joules of heat. The ratio of that is 0.77. And so you can say then that 77% of the ice will melt. Okay. So let's see if instead of asking for a single shot of gin, now you ask for a double shot of gin. Okay. Now, there's going to be now enough gin available so that the gin can provide over 24,072 joules to melt the ice cube before the gin cools, okay, to 0 degrees Celsius. However, once you've completely melted the water's temperature will begin to rise above 0 degrees Celsius. And so we expect that at the end, we'll have just water and gin at some final temperature TF, and that final temperature TF will be greater than 0 degrees Celsius. Okay, so how do we do this problem? Well, we have to say then that the gin is losing energy, and so the energy change of the gin, okay, plus the energy change of the water is equal to 0, and it's equal to 0 because there's no net energy change of the gin in the water because we're in an insulated container. So there's no energy escaping. Okay? And so the energy change of the gin is just what I've been calling Q gin. Okay? And the energy change of the water, well, the energy change of the water is the latent heat required to melt the ice. So that's M ice, L fusion, of the ice, latent heat of fusion of the ice, plus then whatever heat I require then additional to that to raise the temperature of the water up to the final temperature. So that would be M water, Q water, and that's equal to 0. Okay, and so Q gin, Q gin is heat that the gin gives up as the gin cools to some final temperature TF, and Q water is the warming the water from the 0 degrees Celsius just after all the ice melts to TF, okay? And this is the amount of heat that's required to melt the ice at 0 degrees Celsius, okay? And so I can write this then as, I can write then that M ice, LF ice, plus QW, plus Q water. Q water is the mass of the water times the heat capacity of the water times the temperature change, TF, minus the initial temperature of 0, and that's equal to minus Q gin, which is equal to minus mass of the gin, heat capacity of the gin, times the final temperature of the gin minus its initial temperature of 20 degrees Celsius. Okay? And so now you can put the numbers in. This latent, this amount of heat is 2,472 joules that we calculated previously. The mass of the water here, the ice cube has 77.4 grams. The heat capacity of the water now that you're heating up is 4,186 joules per kilogram per Kelvin. The final temperature is TF, and that is equal to minus. Now you have a double shot of gin, so you're not at 34 grams now, you're at 68 grams, so that's 0.068 kilograms. Your heat capacity of your liquid gin was 2,800, and you have a TF minus your initial 20 Celsius. Solving for TF, you get a final temperature of 6 degrees Celsius. So this isn't the coolest gin you can get with this double shot, but it's pretty cold.